You can please mute your mic. Can you please mute your mic, Abdul Rafiq? Okay, let me do it for you. Maybe you can. Okay, so please mute your mic if you don't have anything to add to the lecture. So in the last class, we were discussing the uh, about the determination of Nusselt number over a flat plate, flow over a flat plate. So in that if I recap my lecture from the last class, so it was first of all, we have got, if we talk about the flow over a flat plate, we have got laminar flow in the beginning. Why is that? Because the critical Reynolds number is 5 lakh in the flow over flat plate. So that's why in the beginning, if you see that this x value increases from 0 to some finite value, so in the beginning we will always have laminar flow. So after some critical length, which is x critical, you can see in the figure, then the flow Reynolds number would be equal to half million, and after that the transition to turbulence would start. And then we discussed about different correlations for the coefficient of friction. Coefficient of friction, why we discussed that? Because we want to see the value of drag force on the fluid. So it is for the laminar flow and then for the turbulent flow. And then we discussed about that how we can determine Nusselt number for the laminar flow and turbulent flow. Local Nusselt number means that it depends upon the location that where we are determining its value. So it means that we would have turbulent average Nusselt number for laminar and turbulent flow as well. So we need to integrate these two first to these formulas, and then we can get to the relations shown in the last two equations. So and then we discussed about combined laminar and turbulent effects. So let me clarify it again that maybe I can use whiteboard for that. So let's suppose we have got a flat plate. So Reynolds number in this case, that is defined by rho into u infinity into x divided by mu. Okay, what is x in this case? So x is the distance from the leading edge. So then when we have got Re critical, which is 5 into 10 to the power 5, we would have turbulent flow. So let's suppose that the flat plate is very long, so that in the beginning up till here it was laminar flow at this point, and then after that the flow, it means that from here to here this is turbulent flow, and here it is only in this part it is laminar, right? Now because we have uh, we have seen these correlations in this here. If I go back in this slide, we can see the average Nusselt number correlation for laminar and turbulent. So for this situation where I can say that maybe more than 80% of the length of flat plate, that is turbulent flow. So in this case, I can assume that the entire flat plate flow is turbulent, because 80% means quite substantial. So we can ignore this initial portion, this portion, which is this portion. Right. Okay. So in order to have 80% of the length to be turbulent, what should be the Reynolds number at this point? We call it REL. So if here the Reynolds number is 5 into 10 to the power 5, and after that we have got like this is some length, and then I have got 4 lengths more here, then how much the total Reynolds number at this point should be? Anyone in the class? At the right hand side edge. So for REL definition, so if I can write that, REL is rho into U infinity into length divided by mu, and length is the total length of this flat plane. So my question is that if we have got Reynolds number 5 into 10 to the power 5 at like 20% of the length, so what should be the Reynolds number at the end at 100% length? Anyone? Sharis, are you there?
Yes, sir.
Can you understand my question, or is it too difficult?
25.
25 lakh. Minahil, is that you?
Yes, sir.
Okay, so excellent answer, because if 20% we have got 5 into 10 to the power 5, so after the next 80%, the Reynolds number here would be 2 point, just a minute, 2.5 into 10 to power 6. So if the Reynolds number at the right hand side, it is, if it is equal to 2.5 into 10 to power 6 or more than that, in that case we can say that the entire plate is turbulent. Otherwise, if its value is in between 5 into 10 to power 5 and to 25 lakh, if it is from 5 lakh and 25 lakh, then we need to say that it has got combined laminar and turbulent effect. So for that case, we need to use this relation. Okay, these relations which we have seen for the combined laminar and turbulent effects, right? So I hope that you understand this point clearly, that how do we know that where to use combined laminar turbulent flow formula and where to use this these formula for the turbulent flow. That fully turbulent flow, when the Reynolds number at the edge, right hand side edge of the plate is more or equal to 25 lakh, then we can use this turbulent flow formula. Otherwise, we need to use combined formula, which is 7-24. And if the flow Reynolds number at the end of the plate is less than 5 lakh, then we need to use this laminar flow formula. So if I write these on the whiteboard, the ranges for the Nusselt number formula, just for the clarity. So Nusselt number, just a minute, Nusselt number correlations. If Reynolds number is less than 5 into 10 this Reynolds number REL, which is the Reynolds number at the right hand side, right hand side edge of the flat plate. Okay, if Reynolds number at the right hand side, if it is less than 5 lakh, then we say that because it hasn't reached the critical Reynolds number, so it means that the entire flow is laminar, and we can use Nusselt number correlation for the laminar flow. Now, if Reynolds number is is 25 lakh. Then we say that we use the formula for the combined effect, combined laminar and turbulent effect, and then if we have got Reynolds number greater than 25 lakh, then we can say that we need to use turbulent correlation, turbulent flow, right? So these are the ranges which I have explained because it is not mentioned in the book. So I just thought that it would be a good idea that you can see these ranges. So in the last class we discussed about this combined laminar turbulent effect, then unheated initial length, in which case the sum of the portion it is not heated, so it means that there is no thermal boundary layer but velocity boundary
एक्चुअली
layer.
सर
Yes, Atif.
सर ये सर ये फिगर दोबारा एक्सप्लेन कर दें.
Which figure? Uh,
ये सर नेक्स्ट नेक्स्ट स्लाइड पे जो
okay. This figure?
सर नेक्स्ट स्लाइड पे जो अगली स्लाइड पे सर ये वाली सर ये थर्मल
अच्छा,
बाउंड्री लेयर्स वाली.
अच्छा, ये वाली जिसमें अनहीटेड स्टार्टेड लेंथ है.
यस सर.
Update. Okay.
यस
Thank
सर
you.
यही वाली.
Okay, ji. So in this case, uh, we are assuming a case in which uh, the heating of the flat plate starts from this point, okay, where the mouse cursor is. It means that that up till this point, the temperature of the flat plate it is the same as this T infinity. So it means that there is no thermal boundary layer. Why there is no thermal boundary layer? Because if the T infinity is 15 degrees, so this initial length of the flat plate it is also at the 25 15 degree, 15 and 15, and then if after that length zeta, if we start to give it heat from here, so it means that now the temperature of this flat plate from this point onwards it would be different from the free stream temperature. So when it would be different, then there would be a thermal boundary layer here. But because the flow has been in contact at x is equal to 0, so the velocity boundary layer would start to grow from x is equal to 0. But because the temperature difference starts from after some initial length zeta, so the thermal boundary layer starts after some distance
सर
zeta. Yes.
सर ये थर्मल बाउंड्री लेयर्स बाद में क्यों स्टार्ट हो रही है सर? कांटेक्ट में आ गया तो हीट ट्रांसफर तो होगी ना?
नहीं, वो उसमें assumption यही है कि शुरू ये जो zeta वाली
अज्यूम
लेंथ
किया
है.
सर.
जी बिल्कुल assume ये
ओके
किया
सर.
गया कि ये unheated है, which means that it has got the same temperature as that of atmosphere. तो इसका मतलब है कि अगर T infinity हमारे पास 15 है, तो ये वाला जो टेम्परेचर है जो up till zeta है, up till zeta, this flat plate would have also got 15 degrees. So it means that if there is no temperature difference, it means that there is no thermal boundary layer. But at the same time, velocity boundary layer would be there because we have got the contact at x is equal to 0. But because the temperature difference starts after length zeta, so that's why the thermal boundary layer develops after that length zeta. Is that
यस
clarifies
सर.
your query? Okay, ji, thank you. So,
थैंक यू
so
सर.
this case we can have. So it is just like if I give you a practical example where we can see this, but maybe it is not the exact example. But if you kind of see that whenever you boil some water in a pan, so if you take the handle of that pan as an because that is made of wood or some insulated material, so you can say that this length is for that handle of that pan, and then from here that pan starts from to which we provide heat from the oven at the bottom. So it is kind of that, but it is not exactly that, but you can visualize this from here. Okay, ji. So for this case, the average coefficient we can calculate for the laminar flow and turbulent flow, and we know the distinction between laminar and turbulent flow. And then we discuss about, then when we have got uniform heat flux instead of uniform temperature, then we can use these relations. So these are the relations which are applicable when there is a flux. Like I have just given you example of providing heat from the oven, from some oven to the uh, electric oven to the pan which is placed above it. So that is the example of the flat plate subjected to uniform heat flux. So then we did this numerical in the last class, in which we calculated the drag force, which is basically, first of all we determined that whether the flow is laminar or turbulent. So if you see the critical Reynolds number, that is 5 lakh. So Reynolds number at the edge of this plate is right hand side edge, that is 41,300. So it means that the entire flow over the flat plate is laminar. So it means that we need to use the laminar flow correlations, and we would be using average correlation. So if we use those, then we can calculate CF, and then we know that CF is FD divided by half rho U infinity square into surface area. So then we can calculate the drag force, which is being applied by the fluid force on that flat plate. And then similarly we can calculate the Nusselt number, average Nusselt number, by the relation of laminar flow. So once we get that value, which is 1918, then we can calculate H from this relation, where H is equal to Nusselt number into K divided by length of the flat plate. So if we do that, we get the value of the Nusselt number, which is convection coefficient, which is 55.2 watt per meter square Kelvin. And once we get this, we can easily calculate the heat transfer rate by convection by Newton's law of cooling, which is equal to QHS. Now, because the 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 temperature of the surrounding fluid is more, it is like 60 degree, and the plate is at 20 degrees. So basically we are heating this surface here. So it means that Newton law of cooling can be converted into Newton law of heating. So all we need to do is put Ts minus T infinity in the opposite direction, which would be T infinity minus Ts. So it would be, it means that now the heat is coming into that flat plate rather than going away. So we have got like 11 kilowatt of heat transfer rate. So this was the numerical problem we did at the end of the last class. So now we move forward. So now we do the second numerical. So now we have got air at 20 degree flow over. So we have been given T infinity, which is 20 degrees, flow with a velocity of 8 meter second over a 1.5 meter by 6 meter. So it means that 1.5 meter, here it is mentioned here that 1.5 meter is the width and 6 meter is the length. And we have been also given the surface temperature of this flat plate, which is 140 degrees centigrade. So now we need to calculate the rate of heat transfer from the plate if the air flows. Now we have got two scenarios. For part one, if the flow is parallel to X, and in the part two, we have got the scenario when the flow is in the Z direction, which is into the board along the width, right? Along 1.5 meter, 1.5 meter is the width. So now, first of all, for the part one, when we have got 6 meter long side, then first of all we need to determine the Reynolds number at the right hand side edge. So if we calculate that, but before doing that, we need to calculate the values of mu, rho, and alpha. So in order to calculate mu, we need some um, mean temperature. So as we came across the concept of film temperature, which is the mean value of the surface temperature and the free stream temperature. So in this case, the surface temperature is 140 and free stream temperature is 20. So our film temperature would be equal to 80 degree, which would be 140 plus 20 divided by 2. So 140, okay, maybe it is wrong written here. It should be 80 degree, not 70 degree. So I would make that correction here. So it would be 80 degree, right? 140 plus 20 divided by 2. So it would be 80 degree. So at 80 degree, Prandtl number we can calculate from the table. K for the air we can calculate from the table as well, and this kinematic viscosity. So all these properties can be extracted from the table. So once we get these values, now we are in a position to calculate the Reynolds number at the right hand side edge. So right hand side edge is this one. So for that, Reynolds number would be equal to u infinity or v velocity as it is shown in this figure, v into length of the plate, which is 6 meters. 8 is the 8 meter per second is the velocity, and kinematic viscosity is given. We have just got that value from the table. So in the exam, maybe I would give you these values, but for the practical uh, problems when you go in the field, then maybe you have to get these from the tables. So 8 by 6 divided by this. So you can see that this value is around 18 lakh. So because it is less than 25 lakh,
Combined.
so thank you very much for your input. So it means that now we are going to use combined laminar and turbulent flow effect formula. So if we see that formula, if we go back a couple of slides, then we can see the formula for that. That is 0.037 Reynolds number raised to power zero point 0.8 minus 871 into Prandtl number 1 by 3. So we are going to use this formula for the calculation of Nusselt number. So if you can see that I have written the same formula here, 0.037 Reynolds number 0.8 minus 871 into Prandtl number raised to power 0.334. So if we put in the values, we can get the Nusselt number, which is 2687. Now we have got this value, Nusselt number at 2687. So now we can easily calculate the value of convection coefficient from here, because we know the length of the plate and thermal conductivity of the air from the data. So H would be equal to 13.2 from here. So this is the average convection coefficient, and now we can easily calculate Q, which is HAS into TS minus T infinity 13.2. Now AS would be the surface area on which the flow is happening. So it would be width into length of the flat plate, 1.5 into 6, which is 9. And then if we calculate, so we can get almost 14.3 kilowatt of heat transfer. Now, this was part 1, in which we did consider the flow in the x direction. Now we are going to consider the flow in z direction or along the width. If you see this cursor going upwards, so it is along the width. So in this case, Reynolds number at this edge would be needed, which is this edge. So in this case, Reynolds number would be, length would be 1.5 meter here, not 6. So if we do that calculation, 8 into 1.5 divided by the same kinematic viscosity value. So now we can see that the value comes out to be less than 5 lakh. So it means that if the flow is in the z direction, the the entire plate would have laminar flow if the flow is in that direction, because the Reynolds number which can maximum Reynolds number which can occur, that is at this edge, which is less than critical Reynolds number of value of 5 lakh. So it means that it is safe to use laminar flow Nusselt number correlation. So if we go back, so if we see the average Nusselt number correlation for the laminar flow, we can easily see that is 0.664 Reynolds number raised to power zero point 0.5 Reynolds number 1 by 3. So we are going to use this formula here. So in this case, you can see that I have used 0.664 Reynolds number raised to power zero point 0.5 Reynolds number 1 by 3, and now you can easily see that the value of Nusselt number, because we have used that assumption of laminar flow, it is 408. And if you compare it with the value which you use when we use the combined effect, it is almost, I would say, 6 times less. So if Nusselt number is 6 times less, then the convection coefficient would also be a little bit less in this case. It should be a little bit less than 13.2. So if we see that, because in this case, because length is also less, so it is less, but it is not 6 times less, but Nusselt number value is 6 times less. So because here length is 1.5, in that case it was 6. So when we divide it by here, it comes out to be 8. So what can we conclude from here? Then that when we have got laminar flow, then the mixing of or heat transfer would be less. But if the flow becomes turbulent, then the heat transfer can be enhanced, because there would be rapid mixing of fluid molecules along the layer due to those vortices. So in that case, it would be a quite vigorous heat transfer. So that is evident from the value of H. And then if we calculate the heat transfer, it comes out to be 8.67 kilowatt, while it was around 14.3 kilowatt for the combined effect. So one thing we know from this uh, numerical problem, that the Nusselt number and convection coefficient and as well as heat transfer increases as we move from laminar to turbulent flow. So if we want to enhance heat transfer or mass transfer, then we kind of tries uh, to introduce turbulence, either by putting some roughness on the surface or anything, or we can kind of for the mass transfer. I also told you about the example of rotating some spoon for the sake of rapid mixing of sugar particles in your tea. So that is also kind of a turbulence, or kind of that is an example of mass transfer. So this was the cases for the flow over flat plate. Now we would move on to our next topic, which is flow over cylinder and sphere. So if we consider a flow over a cylinder, we know from our fluid mechanics knowledge that flow comes like this, and then streamlines diverge because of the presence of this, and then depending upon the Reynolds number, they they get separated in the downstream region. On the upstream region, we have got stagnation point, which has got the maximum pressure, and here because we have got flow separation, so it means that it would have low pressure. So we discuss about the form drag in this case. So in the flat plate we only discuss about the skin friction drag, but here we would also have the pressure drag, or we also call it form drag. Okay, and then they meet, and then it would go like this. The flow would always become like this. So it means that for this case, first of all, we need to define the Reynolds number. So what can be the Reynolds number here for the flow over cylinder or sphere? Anyone?
On the left side, it would be less than 5 because there's laminar flow.
No, no. How can we define the Reynolds number in this case? Because for the what do you call it? For the
सर लेंथ का पूछ रहे हैं आप उसमें इसमें क्या होगा
yes, no. Okay, let
The
me
inertial forces
let
over
me
which
yes, let me rephrase my question just for the convenience of understanding. So Reynolds number is basically it is a characteristic velocity into characteristic length into rho. We can put rho here and mu here. Now for the flat plate, the characteristic velocity was u infinity, and characteristic length was x, which is the distance from the leading edge, right? So for the flat plate, we had got rho into u infinity into x divided by mu, right? So it was for the flat plate.
सर इसमें यू तो अप्रोच वेलोसिटी हो जाएगी
जी, वही वाली जो अप्रोच वेलोसिटी, या उसको फ्री स्ट्रीम वेलोसिटी भी, अप्रोच वेलोसिटी को हम फास्ट स्ट्रीम वेलोसिटी कह देते हैं इस केस में, या फिर उसको अप्रोच वेलोसिटी भी, और वो यू इन्फिनिटी होगी। बिल्कुल ठीक है शाहिद। तो फॉर द सिलेंड्रिकल केस, फॉर फ्लो ओवर सिलेंडर, we would have VC would be equal to approach velocity, या फिर उसको हम फ्री स्ट्रीम वेलोसिटी या फास्ट स्ट्रीम वेलोसिटी भी कह दें, ठीक हो। अच्छा जी, व्हाट अबाउट द लेंथ स्केल? अब लेंथ स्केल कैसे डिफाइन करेंगे? उसमें तो हमारे पास एक्स था, या उसको हमने कैपिटल एल भी कह दिया था, जो कि लेंथ ऑफ द फ्लैट प्लेट थी ना, फॉर द फ्लैट प्लेट, बट हियर वी डोंट हैव एनी। व्हाट कैन वी डू?
सर एंगुलर डिस्प्लेसमेंट के हिसाब से
वॉल्यूम ओवर एरिया अगर हम कर दें,
okay, that is also good, very good, but that is very simple in this case. If you see that we have got a diameter, if we have got a sphere or cylinder, if the flow is happening in this direction, the third direction is effectively diameter. So we can have diameter as a characteristic length for the flow over the cylinder. So for this case, we would have Reynolds number definition would be rho u infinity into diameter divided by mu. And here the critical Reynolds number is almost equal to 2 into 10 to power 5. So Reynolds number in this case, when we have got 2 into 10 to power 5, then we would have for the laminar flow it was 5 into 10 to power, for the flat plate it was 5 into 10 to power 5, but now it is a little bit less, because now we have got a great distraction to the flow streams, क्योंकि यहाँ पे फ्लैट प्लेट के केस में they don't diverge much, because that is a streamlined body, but in this case, because we have got a direct impact of flow here, and then there is a great divergence of flow stream, then it means that it can be transition to turbulent flow at much less Reynolds number. So in this case, that value is around 2 lakh. So rather than 5 lakh for the streamlined body like flat plate. So because this is a bluff body, or we can also call it a blunt body, semi-blunt body. So in this case, then critical Reynolds number has been reduced to 2 to power 10 to power 5. Okay. So now we have got Reynolds number. We can have now there are different flow scenarios over a flow over a cylinder. So let's discuss one by one. First of all, we have got flow over a cylinder, and we have got Reynolds number less than 1. So it is called creeping flow. So heavy metals, any heavy metals which can flow. So if there is a cylinder, then what will be streamlined? It would be something like this. The streamline would remain attached. It means that whatever the flow molecule is going there, that would be coming like this. So it means that there is no flow separation. So no flow separation at the downstream region. So it means that no wake region भी कोई नहीं होगा इस केस में, ठीक है, no wake region. So it means that all of the drag on this would be due to skin friction drag, which is CF. So CD would would be 0. Why is CDP, which is the drag force due to pressure, that would be equal to 0. Why is that? Because whatever the pressure is here, almost the same pressure would be here. So the major contribution would be CF here. So because the flow is in contact all along the circumference, so it means that skin friction component would be the most dominant when we have got creeping flow. Okay, when we increase, is there any query regarding this? So for the creeping flow, the skin friction drag would have the maximum contribution, because CD is a combination of CDF plus CDP. So CDP in this case would be equal to 0. So CD drag coefficient would be equal to CDF, right? And so this was the first case when Reynolds number is very less than 1. When we increase it a little bit, like if we increase it beyond Reynolds number 5 and less than 45. When the Reynolds number is in this range, how can we increase the Reynolds number in this case? Only by increasing the velocity. Why is that? If that fluid is the same, then it means that rho is the same, mu is the same, and because if the same cylinder we are talking about, so diameter would be the same. So only thing we can change here to increase the Reynolds number, that is the approach velocity, which is u infinity in this case. So when we have got this this range of Reynolds number, then we have got some kind of flow separation. And we can see some kind of vortices here, and we call it standing vortices. That they are not moving, they are not moving with the flow, but they remain here. Okay, Let me show that figure. Maybe it would be more convenient to do. Just a minute. Can you see this second figure? The right hand side figure, which is the figure B, you can see a kind of floor separation here, and then we can see two vortices here. One is this and one is this on in the wake region, right? So this happens when we have got Reynolds number between the range of 5 to 45. Now, when we increase the uh, Reynolds number from 45, and in this case we would have CDP, there would be some contribution, and it would be more contribution from the CDP, because now we have got the pressure difference between front and back, and then we would have a little bit less contribution from CF, which is skin friction, because in this case, because the flow contact is less, it is not all along the circumference, only up till this point, which is if we start measuring this angle from here, theta. So if theta is being measured from this axis, so flow separates for the laminar, it is at 80 degree, the flow would be separated and it would go like this. Okay. So after Reynolds number greater than 45, 2000, we would have a unsteady flow of vortices. We call it unsteady flow of vortices, which is called von Karman shedding. Now, it is very difficult to explain in words or by the figure. Let me show you a small video for that. That what does it mean by this concept of von Karman shedding? So it means that these standing vortices, they are generated and then they move along the flow because of the inertia of the fluid. So let me show you that in a bit. So if full screen is this one, let me. So if you see, the top figure here is Reynolds number 25, Reynolds number 50, Reynolds number 100, Reynolds number 220. Now the interesting thing is that all these simulations can also be done in your ANSYS software very easily, and people do it for the benchmarking of their numerical scheme. So if you see here, for the Reynolds number 25, they are not they are not having vortices, but now you can see the vortices in the last two, three figures. They start to, these vortices are generated and then they move with the flow direction. So this is called von Karman shedding street. Okay, so this is quite interesting phenomena which happens for all the bluff bodies, the flow over bluff bodies. So we can see this kind of unsteady flow of vortices in the downstream region. So you can see that they are quite nicely looking vortices moving along the flow when we have got Reynolds number around 50. But for the Reynolds number 25, there is no motion of vortices. So it means that the vortices are standing here, right? They are standing vortices for the Reynolds number 25. But for the 50, 100, you can easily hit those more Karman shedding, right? So this was unsteady phenomena, and then if I take you back on this, so here you can see the figure C is the that oscillating von Karman vortex state wake. So those vortices I have just shown you that how they flow along the uh, with the flow if the Reynolds number is more than 50. But if the Reynolds number is less than 50 and more than 5, then we would have standing vortices. and if the flow is Reynolds number is less than 5, then we would have no separation behind the cylinder and the flow would be attached. Right. So now there is a last figure, then laminar boundary layer separation. It happens at 80 degree, but for the turbulent flow, it happens a little bit late. So let me explain it to you that why it is the case. Do you know the art of reverse swing? Anyone, any good cricketer of hardball in your
जी सर,
class?
pressure difference on
Would
both sides of ball.
so why do we get only we polish one side and we keep the other side rough? So then the ball moves towards the shiny side. That is the main crux of reverse swing. So the bowler usually hides the ball so that the batsman cannot see the shiny side because the ball is going to swing in that direction. So that is so here, as I explained, then when the Reynolds number is more than 50, then the flow separates from this point like this. So if we measure the angle from this axis, so if this is theta, which is measuring in clockwise direction from this axis, so at theta is equal to, this is around theta is equal to 80 degree, and the flow becomes separated, and then it goes and then it meets again like this. Right. Now if the flow when it reaches 80 degree, if it becomes turbulent, so what will happen that there would be fluctuations, velocity fluctuations in the flow. Now velocity fluctuation would be in the streamwise velocity and wall normal velocity. So the wall normal velocity means that the molecule which is here, it would turn to oscillate like this. The molecule which is here, it would turn to oscillate like this. So when the flow becomes turbulent, the flow remains attached up till this point is theta is equal to 140 degree. So if the flow is attached here due to these wall normal fluctuations, so due to these wall normal fluctuations, this red portion, this is the region which is attached due to these fluctuations on both sides. So it means that the flow would remain attached, and then when there is theta is 140 here as well, then we would have something like this. Now, one thing you can clearly see that this width is less than this width. Okay? Can you see that? If the flow becomes turbulent and it remains attached, so what will happen that first of all we would have the wake region small wake for the turbulent flow. And second thing that let's suppose we have got the rough. Now we can make a flow turbulent by having roughness here. Okay, roughness. If the flow is rough on the one side, so it means that it would become turbulent and the boundary layer would remain attached up till this point. ठीक है ये 40 लेकिन what if we keep the other side shiny, so in that case the shiny side पे flow यहाँ पे separate हो रहा है. Now you can easily see that because on the top side the flow is attached and on the bottom side the flow is separated, so there would be a drag force in the in this direction. A force would be created in this direction. ठीक है? So that is towards the shiny side. अगर ये शाइनी साइड होगी, अगर ये चीज यहाँ पे ना हो और ये शाइनी हो, तो फ्लो सेपरेट हो जाएगा इस साइड पे, and it would remain attached on the upper side. So when the flow is attached here, so it means that it would have some fluid in this region, so it would apply the pressure in this direction, and the ball would move. If we talk about this ball, so this is shiny side, this is shiny side, and then this is rough side. So rough side, the flow is turbulent and remain attached up till 140 degree, and here it would separate, and at 80 degree now we can see that there is no fluid here, so the ball would move always towards shiny side. So that is also a main reason that why we put a dimple on the golf ball. Can you have you experience of seeing that golf ball? There are dimples on its surface. ठीक है, डिम्पल का मतलब होता है कि वो रफनेस एलिमेंट होते हैं हर जगह पे. उसका पर्पज ये होता है कि when the golfer kind of take his shot, then because critical Reynolds number is 2 into 10 to power 5, right? So if we introduce dimples on the surface of golf ball, then the critical Reynolds number becomes equal to around 40,000, because no because of the this critical Reynolds number that was for the smooth surface, right? So, and when we introduce those dimples on the golf ball, then the critical Reynolds number, that the flow transition occurs at the lower Reynolds number, which is 40,000, right? So that's why, because I have just explained you, or I have shown you that there is a small wake region for the turbulent flow. When there is a small wake region, what is the consequence of that? That the drag force, if you remember the formula for the drag force, what is the formula for the drag force? That is FD, that is equal to CDP into half rho u infinity square into area. Now this area is the frontal area, which is basically this height into the length of the cylinder, or if it is a sphere, then it would be pi d square, 4 pi r square. So if this area where the pressure is different on the front and back, that is less for the turbulent flow, then this drag force reduces. When the drag force reduces due to reduction in the area, area क्यों decrease हो रहा है? क्योंकि that is the area where the flow is separated, so that pressure force would act on this direction, right? So if that area is less due to turbulence, then it means that the drag force which this golf ball would experience, that would be less, and due to that the flow would travel a, a little bit more in air. So that's why they put dimples on the golf ball. Otherwise, there is no sense of putting the dimples on the golf ball. So hopefully these concepts you will also learn in FM2. But because I thought that you haven't learned these concepts, because you haven't gone through that topic in your FM2, so I just thought that it would be a better idea that I kind of tell you here. So, is there any question on this concept? Is it clear or making sense?
जी सर.
Okay, ji. So hopefully these things, because these are very important things, because they are very useful for the design of different applications. These, जी, yes.
सर डिम्पल्स वाली समझ नहीं आई सर, गोल्फ बॉल वाला.
जी, मैं दोबारा समझा देता हूँ. क्योंकि जब डिम्पल्स क्रिएट करते हैं, देन वी आर इंट्रोड्यूसिंग द रफनेस on that ball surface. When there is a roughness, then the transition to turbulence would be very easy, क्योंकि जब कोई चीज रफ होगी तो उसमें क्योस पैदा करना या उसको टर्बुलेंस की तरफ लेके जाना इट वुड बी इजी है. आतिफ, डू यू काइंड ऑफ
Yes, sir.
एग्री विद दिस? ठीक है.
Yes,
When
sir.
that happens, that turbulence happens, then the flow doesn't separate at 80 degree, जो कि ये वाले पॉइंट्स थे. If I highlight it again, these points, ठीक है, by the green dots, so they are not separated here. The boundary layer would remain attached up till this point. Okay, now you can easily see that the wake region where the flow pressure difference is, that area is small for the turbulent boundary layer. Why is that? Because the flow is attached here, so the pressure would be the same on the front and the back because the flow is attached. But for the turbulent flow, that the wake region would be small. Can you see this small wake region here? If I kind of show
Yes, sir.
it with the, so because the wake region is small, so that's why we would have less drag force. That FD would be less, क्योंकि एरिया, ये वाला जो एरिया यहाँ पे है वो एरिया किसके इक्वल है? वो इसी के इक्वल है ना. अगर ये स्फीयर है तो पाई इनटू दिस हाइट स्क्वायर. ठीक है, तो ये हाइट क्योंकि कम है तो टोटल ड्रैग फोर्स भी कम है. टोटल ड्रैग फोर्स व्हेन इट वुड बी लेस, देन द बॉल वुड बी ट्रेवलिंग मोर इन द एयर. ठीक है, सो दैट्स व्हाई वी पुट डिंपल्स. ठीक है.
Okay, sir.
Okay ji, thank you. So now because we have mentioned about the drag force, so we have seen that if we plot CD, which is the drag force with respect to Reynolds number, so let me do that here. So, if we this is CD. Here CD is a combination of CDP plus CDF. So if we draw it for against the Reynolds number, that if we keep on increasing the Reynolds number, so its trend is something like this. And then it dips here. So this is the range where we have got Reynolds number less than, I would say 100, in that range. And then from 100 to I would say 1 lakh or 2 lakh, it remains constant. Now you would be wondering that it means that CD is decreasing with the increase in Reynolds number. So what is your experience that if we increase the speed, if you increase the speed of your bike, the drag force which you experience from the coming air, whether that increases or decreases?
Increases, sir.
It is, but here it is showing the downward trends. Why is that? If I write CD definition here, that is FD divided by half rho U infinity square into area. So this is the definition. Now you can see that the CD is decreasing linearly. It means that CD is decreasing with if CD is decreasing linearly, and here we have got, if I show you by highlighting this, it is the power square. So if something is decreasing, it means that it is 1 upon U infinity function. So CD is a function of 1 upon U infinity. But when we talk about the drag force, so FD would be equal to 1 upon U infinity. From where it came, because CD looks like that it is decreasing linearly in this way. ठीक है, तो ये यहाँ पे CD है, and into half into rho u infinity square. Now this u infinity square would cancel out with this u infinity, and then drag force
सर
is
यहाँ पे यू इन्फिनिटी मल्टीप्लाई नहीं होगा
कहाँ पे?
FD में FD में
FD
1 ओवर यू इन्फिनिटी क्यों लिखा है?
हाँ जी, क्योंकि CD अगर यहाँ पे देखें ना इस रेंज में शारिस, CD इज इनवर्सली प्रोपोर्शनल टू u infinity, क्योंकि रेनॉल्ड्स नंबर के अंदर u infinity आता है ना शारिस।
जी सर, जी सर।
तो इसका मतलब ये हुआ कि CD is directly proportional to 1 upon u infinity in this range. Do you get it?
जी सर।
Now I have put it instead of CD, I have put 1 upon u infinity here. Okay, and we have taken the denominator here and multiplied it here. Now you can see that because we have got u infinity square here and u infinity in the denominator, so u infinity in the denominator would be cancelled out with this power square, and FD is indeed increasing with increase in the increase in velocity. So that is the same thing which you experiences on your bike. Okay, when you increase the speed from 10 meter per second to maybe 30 meter per second, you experiences more kind of the flow coming on to you. Okay, so it means that that is a true thing, that this drag force would increase with the increase in velocity of the bike, or the flow velocity in this case. In this range, which is this range, in this range, FD is function of u infinity square now. Okay? It means that the drag force would increase very rapidly if the flow is in the range of if the Reynolds number is in the range of 100 to 1 lakh or 2 lakh. Now after that we see a sudden decrease in CD, which is this green line. So that is when the flow changes from laminar to turbulent. Okay? So that sudden dip that we want to create for the golf ball. Okay? Why is that? Because when there is a sudden decrease in CD value, it means that the FD value, the drag force, would also decrease, and the golf ball would travel more in the air. So that is the whole purpose of putting dimples on that. That is not for the aesthetic look or the beauty of the golf ball, but rather it is a necessity because we want that golf ball to travel more for a given striking force of a golfer. So that's why we kind of put dimples on the golf ball surface. Okay, so that is the things which I wanted to explain. But up to now, you would be wondering that I am explaining just the fluid flow phenomena, but not. I haven't talked about anything about the heat transfer up till now for the this cylinder. And that is due to the fact that if I don't explain these things, you are not going to understand the Nusselt number variation for the flow over a cylinder. So, okay, let me now take you through the slides, because I have used the whiteboard up till now. So, for the characteristic length for the flow over cylinder, I have told you that is the external diameter, and the critical Reynolds number is 2 lakh, and then the drag force is primarily due to friction drag at low Reynolds number when there is no flow separation, and then due to pressure drag, which is at the higher Reynolds number when we have got Reynolds number more than 5,000. So uh, because then we have got flow separation and these things. So this is the graph I have just explained you now. I think 1 minute before, you can see this is the graph of CD versus Reynolds number for the cylinder and sphere. So you can see the linear decrease of CD up till 100, and then you can see kind of a constant value in between 100 to 10 to power 5. So these are the things. So here CD increases with U infinity square. That is the function. It increases rapidly, that drag force. Drag force increases rapidly, but CD remains constant, and then there is a sudden dip when the flow transition from laminar to turbulence due to that critical Reynolds number at 2 into 10 to the power 5, right? So this I explained now. And now this is the creeping flow which we discussed before, that in that case Reynolds number CD is 24 divided by Reynolds number. It means that CD is a function 1 upon U infinity, that is inversely proportional to U infinity, and then at Reynolds number 10 separation starts, and then up till 50 I have told you about the standing vortices, and then after that we have got von Karman shedding speed. The drag coefficient 1000 to, like, it should be 1 lakh here. The drag coefficient remains relatively constant, and then I have explained you that for the laminar flow, this wake region at the back side of the cylinder is more. You can see easily that this wake region is more, but for the turbulent flow, because the flow remains attached up till this point, which is theta is equal to 140. If we start measuring from here, so because the flow remains attached, so the wake region is less, so the total drag force would be less. For the laminar flow, it separates at 80 degree, so that's why the wake region is more. So these things, they are again explained. So this slide I have borrowed from your Munson's book, just to tell you these things clearly, and we have also seen a little video for the von Karman shedding street, which is in the range of Reynolds number 50 to 1000. Okay, so now I have also explained you the golf ball. So this is the for streamlined bodies, surface roughness increases the drag coefficient. That is true, because if the roughness is more for the streamlined body, the drag force would increase. But for the bluff body or the blunt bodies, the surface roughness decreases the drag coefficient. Why is that? Because when the flow becomes turbulent, the wake region becomes less. So you can see here the value of CD. It decreases sharply at 40,000. This dotted line in the beginning. And if the flow separation, if the flow turbulence transition is happening at some later stage, you can see this solid line that is it is sharply decreasing at 2 lakh if it is a smooth surface. ठीक है, 2 lakh के ऊपर देखें तो CD की वैल्यू it has decreased very sharply due to that laminar to turbulent transition. Okay, when epsilon upon d is equal to 0, when the critical Reynolds number is 2 lakh, so the flow transition happens here. But for the golf ball, the flow transition happens at 40,000. Why is that? Because we have put dimples on the surface, so that accelerate or it makes the critical Reynolds number almost equal to 40,000. So in that case, the flow transition happens, and then due to that, FD value decreases, and then the flow travels more in air. So up till now we have covered only the fluid flow portion for the flow over a cylinder or sphere, which you would hopefully you would repeat it in the in your ongoing course of fluid mechanics too. Okay. अच्छा जी, now we have discussed flow separation, occurrence of recirculation in the wake region, reduction in the downstream velocity, which is also happening in the wake region. And wake region is the flow region where the effect of the object presence is felt. it is in the downstream area. You can easily see that wake region when you see some boats flowing through some river. You can see easily that the wake region is there in the downstream area of that. So viscous flow effects are very dominant in the separation region, boundary layer, and wake region in case of flow over cylinder. Now, I think we can continue this here, and now I am going to explain the Nusselt number variation over a cylinder. Now we are taking theta is equal to 0, this stagnation point, and then theta would increase to 180 degree if we move to the rear of this sphere. So if I show you the variation of Nusselt
ब्रेक
number for that,
नहीं है आज
Isharit,
मैंने ब्रेक नहीं होगी आज
if you want to take a break, we can have a break of 5 minutes and then we can come back.
सर
So
10 कर दो
let's
सर
सर
then whether it would be better if we study for like 10 minutes more and then we would call it a day.
ओके सर
ओके सर
Whether that would
ओके
be
सर
better or maybe we can have a break and then we can have 20 minutes more.
नो सर ये 10 मिनट ठीक है
देखे ना
4:30 पे छोड़ दीजिएगा
साथ ही वो
सर अभी
जिसे
करते
कहते
हैं
हैं democracy is the best thing. So majority of the people have said that we go with the option one. So it means that we continue with the lecture. So that's good. So it can extend to 15, but not more than that. Okay.
सर अब ये
So
आप गलत कर रहे हैं
आप देखें ना थोड़ी सी बार्गेनिंग चिप्स होती है ना so that I have taken advantage of that. So if you look at this figure, this is now the thing which is more concerned with us. So for the Nusselt number, theta is equal to 0 is this stagnation point. So from if you see that from the theta is equal to 0, Nusselt number would decrease up till 80 degree. Okay? If we talk about these two curves which are on the lower side. So Reynolds number for one it is 70,000 and for the other it is 1 lakh. So if you see that the Nusselt number decreases up till 80 degree. Why is that? Because the boundary layer grows. When the boundary layer grows, partial t by partial y decreases along the circumference up till 80 degree. Now after 80 degree, there is a sudden jump you can see in these two curves. That jump is because the flow is going to separate. When the flow separates, then because there is a backflow in this region, so there would be intense mixing of the fluids. So that's why the heat transfer rate would increase when there is a फ्लो सेपरेशन एट थीटा इज इक्वल टू 80 डिग्री ठीक है एक्स एक्सिस पे थीटा है जो कि एंगल है फ्रॉम 0 which is stagnation point to 90 degree which is top surface of this and 180 degree which is the back side ठीक है लेकिन if you see that these curves are different when we have Reynolds number of 1,40,000 1,70,000 and 2 lakh so these are the curves when we have got flow turbulence at 80 degree. So because they are we are considering some rough surface sphere, so it means that the critical Reynolds number is less than 140,000. So you can see there is a sharp jump in Nusselt number at 80 degree. Okay, that jump is due to if you see here that jump is due to flow converting from the laminar to turbulent. It is not being separated, but rather it is being flow turbulence transition from the laminar to turbulence. So you can see very drastic increase in Nusselt number. So then after 80 degree, the turbulent boundary layer grows, so Nusselt number decreases, and then at if you see 140 degree here, the flow separates, and when the flow separates, there is again the rapid mixing of the fluid, and then again the Nusselt number increases. Yes, any query? Because someone unmuted his mic, maybe I thought that there is a query. So there are two peaks, there are two troughs here. Okay, the first trough for the higher Reynolds number cases is when we have got the flow transitioning from laminar to turbulence, and then there is a second trough here that is due to flow. At this point the flow changes, flow separates from this cylinder surface at 140 degrees. So that's why there are two kind of troughs here and one peak, but in this case there is only one trough for the laminar flow, because in this case at 80 degree the flow would detach from this surface of the sphere or the cylinder. ठीक है जी, ये तो हमने पढ़ ली एक जनरल अंडरस्टैंडिंग के नसल नंबर वुड इंक्रीज व्हेन द फ्लो would become turbulent or it would become separated from the surface of the cylinder or sphere. So but we are more interested in the average values of Nusselt number. So then so this was physical understanding, yeah, explanation of the phenomena. Now we move on towards the empirical correlation for the Nusselt number in case of a flow over cylinder. So for the flow over cylinder, the Nusselt number would be equal to this complex relation, and it is applicable when the product of Reynolds number and Prandtl number is more than 0.2. So we can calculate Nusselt number from this, and then if there is a flow over a sphere, then we can calculate Nusselt number, average Nusselt number from this correlation. Now the definition of Nusselt number is a little bit different. You can see Hd upon K rather than HL upon K, which was for the flat plate. Now we have got diameter of the pipe. So Nusselt number definition is different for flow over cylinder. And then we can also see that we have got Reynolds number and Prandtl number dependence here, and mu infinity is the viscosity near the away from free stream viscosity of the fluid, and this mu s is the viscosity of the fluid at the surface, right? So these are the formulas when we have got cylinder and sphere. But what if we have got a 2D object which is not of cylindrical shape, rather than that is a duct, or rather that is some other pentagonal shape, square shape, या फिर kind of flat plate. So let me kind of do a little bit of zoom in here, and then you can see that table a little bit more clear. Let me do that. So if we have got this table, now you can see, maybe it is not clear. Now if we have got a circular cylinder and we have got a gas or liquid flow, then if the Reynolds number is in between 0.4 to 4, then we would use Nusselt number average Nusselt number correlation of 0.989 into Reynolds number 0.330 into Prandtl number this. And if the Reynolds number keep on increasing, these coefficient of this C value and M value, they would change accordingly, but the N value, which is 1 by 3, that would remain the same. So Prandtl number is not a strong function of Reynolds number, rather it depends upon the thermal properties. So that's why Prandtl number is not changing, but Reynolds number, the power of Reynolds number and this coefficient C value is changing. And then for the, if the that 2D body is a square, it means that it is this profile, it is the same in the third direction. So it means that we have got a duct into the board. So in that case, if the flow is gas, then Nusselt number can be determined by this relation. Uh, C value is 0.1 and M value is 0.675, and then if it is a square tilted at 45 degree, then we can see, and for the hexagonal thing we can see the relations are different. And then vertical, if the flow is over a flat vertical plate which is extended in the third direction, which is into the board, for that Nusselt number is this. Again, you can see that all these correlations are the empirical correlations, and we can find the value of Nusselt number if we consult the relevant the corresponding empirical correlation. So, because why they are empirical correlations, let me reiterate, because these Reynolds number ranges are include turbulent flows, so that's why we cannot have the solution of those governing equations. So rather we conduct experiments by taking this power law formula, and we determine the values of C, M, and N by the conduct of experiments. And people have done those experiments and tabulated the data for you, the values of C, M, and N for different practical cases uh, in this table. And in the next class, which is tomorrow, we would be having the numerical of this, and then we would be discussing the quiz number 3, which is from chapter number 4 and chapter number 5, and then again the process is the same. At 10 past 4, it would appear in your assignments, and then you would have 15 minutes to do it, and you can do it up till uh, up till 20, 25 past 4, and then you have got 5 minutes to submit it.